All right, hello again. So last time we left off talking about the relationship between inputs and outputs in the short run, right? And there wasn't that much to talk about because in the short run, we only really have one input we can control, which is labor. What we're going to be doing today is considering the problem we face in the long run when we could produce output by changing labor or by changing capital. And in particular, we're going to think about what we call the plant manager's problem last time, which is to say, how are we going to produce a certain amount of output as cheaply as possible? Now, the reason I think of this as the plant manager's problem is you could imagine that you're in charge of a factory, you get a call from your boss saying, we need 16,000 Honda Accords this month, and you have to decide, how am I going to produce 16,000 Honda Accords with the lowest possible cost, right? You have a production target you have to meet. The question is, what combination of labor and capital will allow you to meet that production target as cheaply as possible? Cool. So let's think through this by imagining some particular production function. So let's say we've got F of labor and capital equal to some fairly standard Cobb-Douglas, something like L to the 1/2 times K to the 1/2, right? And we're told by our boss, let's say we're on a potato farm, we're told by our boss we need to produce Q equals 4, right? So let's say we need to produce 4 tons of potatoes. And we want to do so as cheaply as possible, given that we've got some wage rate and some rental rate. Just making things up. Let's say that the wage rate, we need to pay our workers $20 an hour. And the rental rate, we can rent a tractor for $5 an hour. Cool? Cool. Okay. So how are we going to go about trying to solve this problem? So we want to produce Q equals 4 as cheaply as possible. Right? So I'm going to propose a relatively straightforward way of attacking this, which is to say, let's first figure out all of the different ways that we could produce 4 tons of potatoes. Right, all the combinations of labor and capital that will be, let's say, greater than or equal to 4, right? That will meet our production quota. And then second, pick the cheapest one, right? Pick the cheapest option. Right, seems straightforward enough. We want to figure out how to produce 4 tons of potatoes as cheaply as possible. Let's just look at the set of options that will produce 4 tons of potatoes, pick the one that costs the least. So we'll start with this first part, right? What are all the ways that we could produce 4 tons of potatoes? So to do that, right, we're going to need all the L and K. So then, right, L to the 1/2 times K to the 1/2 greater than or equal to 4. Right, which is of course to say that L times K greater than or equal to 16, right? Just square the whole thing to make things easier. So if we're going to graph this, right, I'm going to put labor on the horizontal and capital on the vertical. Let's just consider various combinations that'll give us L times K equals 16. So if L was 1, for example, K would have to be 16. Right, if L was 2, K would have to be 8. Right, if L was 4, K would have to be 4, and so on and so forth, right? If L was 16, K would have to be 1. So if we graph this thing, we'll end up with some nice curve like this, right? This is going to look very familiar to you because it looks just like a Cobb-Douglas indifference curve. And the reason it looks just like a Cobb-Douglas indifference curve is because it's describing a Cobb-Douglas production function, right? What this is going to be is basically all the combinations where I have Q equal to 4. So what's going on here? what's happening is I've divided all the combinations of labor and capital into the combinations where I can produce at least 4 units of output. This is going to be feasible. And all the combinations where I can't. Right, in exactly the same way that an indifference curve would separate better from worse. And we'll call this thing, right, because of the fact that it's representing all of the combinations of labor and capital that produce equal quantities of output, I'll call this thing an Iso Quant. Iso meaning same, basically in Greek, and quant meaning quantity, right? So this thing is my Iso Quant. Now, there's a couple things I want to point out about isoquants before we move forward. In particular, the ways in which they are and are not the same as indifference curves. Because, of course, this looks so much like an indifference curve, and so much of our intuition is going to follow forward from what we've learned about indifference curves. So the first thing I want to point out is that when we drew indifference curves, right, we started by thinking about preferences. We said people prefer A to B and B to C. We used that to draw indifference curves. And we said the indifference curve is real, right? Then we said, now that we've drawn this indifference curve, we can label them from worst to best with some number, right? Where lower numbers mean lower levels of preference, right? Lower indifference curves are worse than higher indifference curves. And we called that labeling system a utility function. So the indifference curves were real. The utility function was a representation of those indifference curves. In this case, as we talked about last time, right, this is really important to remember. The production function is real, right? And it's being represented by the isoquants. So the values coming out of our production function have real meaning, right? They correspond to real quantities of output. The isoquants are ways of graphing these production functions. So the first thing is isoquant is a graphical representation of production function, which in itself is a real thing and is the thing that we actually care about, right? In a way that utility was just a tool we didn't actually care about. As a consequence of this, right, monotone transformations of our production function will not change our isoquant for the same reason that they wouldn't change the shape of our indifference curve, but they do represent different things. They are meaningfully different. So if I doubled my production function, right, let's say that I had f tilde of L and K equal to 2L to the 1/2, K to the 1/2, right? If I drew an isoquant here for L tilde, F tilde, it would be exactly the same as the isoquant I've got on the board, except here it would represent Q equals 8. The important point here, Q equals 8 and Q equals 4 are not equivalent, so this would have the same isoquants, but a different meaning. Another way to think about this is that when we label our isoquants like this, those labels are intrinsically useful and important in a way that labeling our indifference curves with utility values was not. Okay, awesome, awesome, awesome. The second big thing to remember, when we drew our indifference curves, they were separating better from worse. In other words, the indifference curve was telling us what our objective was, right? If we drew, let's draw a little picture here, right? If we drew a budget constraint like this, and an indifference curve like this, right? Everything here was better than everything down there, right? Our indifference curve told us, out of the options that were available to us, which option was our favorite. Isoquants aren't doing that. Isoquants are actually doing the other job. So what isoquants are doing is they're telling us which options are available to us and which options are not available to us. So isoquants actually take the role, when we're minimizing cost, not of indifference curves, but of budget constraints, right? Isoquant is our constraint. Tells us what's feasible, and is our constraint. Right? It looks like an indifference curve, but it's doing the job of our budget constraint. Okay, great. And then the last thing, we'll talk about this a little bit later. We're going to put this on ice for a minute. But the third thing to remember is that because the fact that these quantities are meaningful, the distance between isoquants is a meaningful thing. In other words, right, if we draw indifference curves, if I said that my indifference curve for u equals 4 was right next to my indifference curve for u equals 5 million, that would tell us absolutely nothing about my production or my preferences, right? Because 5 million is an arbitrary number. But if I know that the amount of labor and capital it takes to make 4 units of output is very close to the amount of labor and capital it takes to make 5 million units of output, that's real information. Okay, right, so great. So the really important takeaway, we've said a lot here, the main thing to think about is that this isoquant is going to take the role of my budget constraint, right? Everything above is affordable, everything below is unaffordable. So I've already done the job here in this graph of doing the first part of my two-step process, right? I figured out all of the different ways that you can produce 4 or more potatoes. So now that we know all the ways we can produce 4 potatoes, that brings us to the second piece of this, right? Which is which of these options is cheapest? In other words, how are we going to produce these potatoes as cheaply as possible? So the first thing I want to do to think about this is to think about, for any arbitrary amount of labor and capital, what is our cost, right? How expensive is it, right? Expensive being the opposite of cheap. And the answer is going to be, right, our cost is going to equal, well, the amount that I spend on labor plus the amount that I spend on capital, right? The amount I spend on labor is going to be W times L. The amount that I spend on capital is going to be R times K, right? So I'll say C of L and K is going to be WL plus RK. Because I've got a wage rate of 20 and a rental rate of 5, it's going to be 20L plus 5K. Cool. So this can basically give us our score, right? For any candidate we select, this will tell us, how much does that candidate cost us, right? Then we could potentially try each point on our isoquant and find the one that has the lowest cost. So that doesn't sound like a super effective strategy, but let's try it, right? Let's start that way and see if we can think of something a little bit better as we go. So I'm going to pick a candidate. Let's try L equals 4, K equals 4. Right? That's going to work, right? Because 4 to the 1/2 times 4 to the 1/2 is 4. So we'll produce enough potatoes. Cool. So how much would that cost? C of 4 and 4 would equal 20 times 4 plus 5 times 4, right? Which is going to be 80 plus 20 equals 100, right? So if we spend $100, we can get to our 4 potatoes by buying 4 workers and 4 machines. Cool. So now we just need to know, is that as cheap as possible, right? We know how much it costs, but let's think about whether it's our best option. And to do that, I'm going to use this to graph everything that's cheaper and everything that's more expensive than 4 workers and 4 units of capital. So what I can do is I can say, let's say stuff that costs $100 will be anything where 20L plus 5K, right, equals 100. With me so far? So if I graph this, I could have 20L plus 5K equal 100 if I had 5 workers and no capital. Or if I had, what would it be? It would be 20 units of capital and no workers. Right? and of course, if I had 4 and 4. So if I graph this thing, it would look something like this, right? This is going to be C equals 100. And everything up here is going to be more expensive, right? If I added a worker, didn't take away any capital, I would certainly increase my costs, right? So everything up here has got to be more expensive. Everything down there is going to be cheaper. I forgot I only had two good colors. So everything below this, right, is going to be cheaper than $100. Okay. This makes sense, right? If I pay fewer workers, right, 4 workers, for example, is less expensive than 5 workers. I'll call this thing an ISO cost curve. Right? ISO, again, for same. Everything that costs the same amount. And my ISO cost curve, right, it's going to be a straight line because I'm paying the same amount for every worker and the same amount for every unit of capital. But it's actually going to play the role in this problem of my indifference curve, right? Because it tells me what I like better, what I like worse. If my goal is to get my 4 units of potatoes as cheaply as possible, right, my 4 tons of potatoes as cheaply as possible, I'm going to want to be on the lowest possible ISO cost curve, right? I want to go this way. So given this, given what we've done, is 4 workers and 4 units of capital the cheapest way for me to produce 4 tons of potatoes? I'll get out of the way. So remember, everything above my Isoquant can produce 4 tons of potatoes. Everything below my ISO cost is preferable to me, right? It's cheaper. So the answer is going to be no. No, this can't possibly be my best choice because I could choose something like this, right below my ISO cost curve and on my Isoquant that would get me the same number of potatoes at a lower cost. Awesome. So if my goal, right, is to get on the lowest ISO cost curve, given at or above, on or above, I'll just say on Isoquant, right? Essentially, I've got a problem that looks just like the constrained optimization problems that we did as consumers, except flipped, right? I have this curvy constraint. The Isoquant's my budget constraint. The ISO cost takes the role of my indifference curve. And instead of trying to be as far out as possible, right, instead of trying to maximize my utility, be on the highest possible indifference curve, I want to be as far in as possible, right? I want to minimize my costs, be on the lowest possible ISO cost curve. Awesome. Okay, so what's this going to look like? What's it going to look like when we find an optimal solution? Well, and this might blow your minds, right? You might be shocked to hear this, but there's really going to be 2 possibilities. Either we're going to have an Isoquant like this, and an optimal ISO cost curve like this. In other words, have our ISO cost only touch our Isoquant at one point, somewhere in the interior, or we'll have an Isoquant like this, right? And have an ISO cost curve like this, right? In other words, we could have a corner solution. Both of these cases are going to be solutions, right? Because we've got everything feasible, everything better, and nothing that's better is feasible, right? Nothing is below our ISO cost curve and on our Isoquant. Same deal here, right? We've got everything better. I'm sorry, everything, oh my goodness. Everything feasible and everything better right? Nothing that is better than our optimal point is feasible, right? So optimal point here, optimal point here. Excellent. And what are the conditions going to be, right, in order to get this? Just like interior and corner solutions before. Right here, we're going to have the slope of our isocost and our isoquant curve be the same, and to be on our isoquant. Here, we'll need the slope to either be steeper of our isocost to be at a vertical, or less steep to be at a horizontal. And again, we're going to need to be on our isoquant. Awesome. So in the next video, we're going to talk about how to look for these two kinds of solutions mathematically.